All right. Now, last week we talked about the revised simplex and how it works, and actually how the matrix form is constructed. And this week we're going to do the iterations, and we're going to see how we use it to achieve the optimal solution, and how we can use it for other stuff as well. Now, we will start with the Dakota example, something we already know, and hopefully something you have already, tried to find the matrix form for, but still, if you have missed your homework, it doesn't really, change what we're going to do here. You're going to see everything being done one by one. Now, Dakota example is something we already know. We have three decision variables, x1, x2, and x3. We have four in this format, four constraints. We are adding the table demand constraint as well. So we have four constraints in here. So we will get four more s values, the slack variable values from here, s1, s2, s3, and s4. And as you can see, our x vector, the variables vector, is going to be x1, x2, x3, s1, s2, s3, and s4. So it's a four slack variables and three decision variables, a 7 variable vector. Okay. And we have the objective function constraints, objective function coefficients, which is the C vector, which is the 60, 30, 20, and 0, 0, 0, 0, because the S values have 0 coefficients in the initial table. And then we have the over here the constraint coefficients, which is the A matrix, and we can find this matrix from here. So it's 8, 6, 1 for the first three columns, and 4 to 1.5 to 1.5, 0.5, 0, 1, 0, as you can see over here. And then we have the S values, which is the identity matrix at the initial table anyway. So we just copy paste the identity matrix over here. And then we have the right-hand side values. So 48, 28, and 5. Those four matrices are vectors, however we choose to see them. Three of them are vectors, one of them is a matrix anyway. So all vectors are matrices. So we can just call them a matrix, all of them matrices anyway. But still, these four matrices are what we are going to use after we divide them into parts. We have to find the, as you can remember, the basic variable coefficients and non-basic variable coefficients for both the C and the A vectors or matrices. Now, to do that, we have to decide which decision variable or which variable is a basic variable. We have to check which one it is. But as we're going to do this normally, step by step, starting from the initial table, we know that the S variables are the basic variables and the X variables, X1, X2, and X3 are the non-basic variables. So we can just divide these matrices into two parts. So as you can see here, these are the basic variables, S1, S2, S3, and S4, and these are non-basic variables, X1, X2, and X3. So the coefficients for basic variables in the objective function are 0, 0, 0, 0. And, this is because of the S variables. Because the S1, S2, S3, and S4 are the basic variables, the corresponding coefficients, which are 0, 0, 0, and 0, are the CB, vector. They make up the CB vector. And X1, X2, and X3 are non-basic variables. Hence, 60, 30, and 20, which are coefficients for x1, x2, and x3 in the initial table, are the non-basic variable coefficients vector to see. And now we have the B, the coefficients in the constraint for the basic variables, which is the because it's the initial table, which is where the S1, S2, S3, and S4 have the identity matrix by itself. This is the identity matrix. And then we have N, the non-basic variables coefficients in the constraints. So all these four matrices will be useful in the operations to come or the iterations to come. Now, to start, we have to find which non-basic variable will enter the basis, will become a part of the solution, and which basic variable will leave. As with normal simplex, it's the same thing we are going to do. To do that, we have to find out where we can go, okay? How we can do this. Oh, okay. One more thing before we start the iteration, of course, we need to see which we need to see the inverse of B so that we can make the calculations, of course. But as B is the identity matrix, the inverse will be the identity matrix anyway, so it won't change. So we can have the identity matrix with us. And now we will say that, okay, we will assign a new, we will use a new vector, which is going to be W, and we will say that CB times CB multiplied by B inverse is going to be W. And we already know that CB, the basic variable coefficients for the objective function, are all 0. So it's going to be all 0 as well. And now we have this part. Now, this is where we find the optimality condition. Remember that one, I hope. This calculation is going to give us the coefficients for non-basic variables in the current iteration. The current iteration is the initial step, so it's going to be the same values for Cn, only the negative values for it. So it's going to be minus 60, minus 30, and minus 20. And as you can see over here, this calculation gives us minus 60, minus 30, minus 20. So we already know which non-basic variable we're going to pick. We're going to pick the non-basic variable with the most negative value, which is minus 60, which is x1. So x1 will enter the basis. Okay, it's the same thing we have done for normal simplex, for simplex algorithm. From here, we're going to do something different, just a bit different. We're going to calculate for only minus 60, for only x1 values. We're going to see what I'm talking about. Now, before we start, as we know that x1 is going to enter, all we need to do is just make the calculations for x1 only. So we have x1, x2, x3, those three decision variables, those three non-basic variables. And when we make the calculations, the row operations, we actually calculate every value for x2 and x3 as well, but we don't need them. We don't calculate for x1, so we don't need to calculate for n values. Instead of n values, we're going to calculate for aj. So we already know the B minus is the identity matrix because it's the same as B. There's no change in that. And aj is, let's go back, this one, or go back further, this one over here, because when we formulate n, you see x1, x2, and x3, this is xn, this is the order. The ordering is very important here. We can shuffle this order. We can say that, okay, x1, x3, and x2, non-basic variables can be shuffled like that. We can shuffle the basic variables as well. It's up to us. But if we shuffle these variables, x1, x3, and x2, for example, like this, then we have to shuffle Cn and n in the same order as well. So Cn is going to be 60, 20, and 30. If x2 and x3 switch places, their coefficients or their vectors should switch places as well. So we already know that it's 8, 4, 2, and 0. This part belongs to x1. So this aj, which means the coefficients in the constraints for only that variable, is going to be 8, 4, 2, and 0. Which is like this over here. So this multiplication, this matrix multiplication will give us this vector anyway. So 8, 4, 2, 0, this is the same thing. From here, we need to find the pivot point, okay? To be able to find the pivot point, we have to make the ratio test. So we have to take the ratio into consideration, which means that we're gonna divide the right-hand side values by this value. This B inverse times aj is our current, whichever step we are. It's our current values in the constraints, current coefficients in the constraints. As we are in the initial steps, they are the same as the starting one because it's the initial step anyway. We haven't done any iteration yet. You will see what I'm talking about in the next iteration after this one is done, but still it's the same, starting iteration. So they are the same values, 8, 4, 2, 0. The right-hand side values are, well, they're the same anyway, 48, 28, and 5, because what we need to do is just multiply B minus B inverse with the small b, the right-hand side values, so that we get the current right-hand side values, but it's the initial step, so they are the same as the starting values, 48, 28, and 5. So what we need to do is just ratio test, do the ratio test, so divide 48, 28, 5 by, respectively, 8, 4, 2, and 0. Well, 48 over 8 is 6, 20 over 4 is 5, 8 over 2 is 4, and 5 over 0 is infinity, so we don't need to check that one. And the smallest ratio is in the third row. So let's go back and check third row. So which means that our third basic variable will leave, S1 first, S2 is second, S3 is the third. So S3 will leave, X1 will enter. Okay, this is the simple pivoting part. We know who is going to leave, who's going to enter. But after that one, all we need to do is just change the bases, change these two, vectors, these two sets, let's call them, because they are sets. And by changing these two sets, you will just take x1 and put it over here. You will take s3 and put it over here. And every value respectively down here will change. So when I change s3 and x1 coming over here will mean that this value of 60 will replace this value of 0. And this value of 0 will replace this value of 60. So they will just change places. Also, 8420 will replace 0010. So 8420 will hop over here, and 0010 will hop over here. They will just trade places as well. Okay, this is what happens when you take a variable, a non-basic variable, and have it enter the system, and take the basic variable in the system and make it leave the system. You just trade places, every value of it. Okay, so this 60 will trade places with this 0, and this 8420 vector will trade places with this 0010 vector. So when we make that change, we will have to find the B inverse once again. Now, we can find the B inverse by taking the inverse of B, but this is going to take a long time as the iterations get, complexer and more complex and more complex. So all we need to do is just find the easier way. Now, that easier way exists. What we need to do is normally, when we are making the pivot, we are just making sure that this value of 2 becomes 1, and every other value above and below it becomes 0. You remember that part, I guess. So when we make that iteration, we just change the table, all of the table. Now what we need to do is just make the iteration, but while we are making the iteration, we will also make all those row operations. We will also make that iteration, all those row operations in the current B minus B inverse as well. Now, this is how it happens. We change this 8420 into 0010. But when we are making the operations to change this, we are making those same operations to the B inverse as well. So for example, to make the iteration, the first thing I have to do is just divide 2 by 2 so that it becomes 1, right? So when I'm dividing this by 2, I'm going to divide this row by 2 as well. So it will become 0, 0, 0.5, and 0. Then, as this is 2, from this, I can still use the initial table. As this is 2, I can just multiply this by 2 and remove it from, subtract it from the second row so that this one will become 0. So I can do the same thing here. Multiply it by -2 and add it here. So it becomes -2. And to get rid of that 8, I have to multiply this by -4 and add it over here. So this one will become -4. So as you can see, this is now, this part, this matrix is now the new B inverse. So instead of, as I said, we will just replace the B value over here. The 0010 will be replaced by 8420. And then we can find the B inverse from this new B, but we don't need to do that. Instead of doing that, we can just use our iteration itself. Okay. So what we need to do is just change this column into this column, part of the identity matrix. Remember that one. And this one needs to be 1 because we are replacing the third constraints basic variables. So this one will become, this part will become 1 and the others will become 0. And while doing that, we can just change the B inverse as well. We don't need to calculate it from scratch. We can do that, but it would take a lot of time every time if I do it every time. Instead of doing that every time, we can just use that current B inverse and change it into the next one when I'm changing this part of the constraints coefficients into the identity matrix. Now, when I do that, I will have the new B inverse, and I can use that B inverse to calculate the next step. What do I need? Well, first of all, I need to find the W, the CB times B inverse part. Now, the CB has changed. As you can remember, it was all zeros, but now it has a 60 in it. So 0, 0, 60, 0. And the B inverse has changed into this matrix. Now, from this multiplication, we will get 0, 0, 30, 0. It's expected because we had a lot of zeros. So yeah, 0, 0, 30, 0 is our new W. We also need to calculate the optimality condition. Is this thing optimal? So we just need to, instead of writing CB times B inverse, we can just write this 0,030 over here. And we already know the n. Check out, this n has changed because the new non-basic variable is S3, so S3 will have its own coefficients written over here. So the new n is over here. And then we need to we need to subtract the new Cn, which is 0,3020. This 0 is over here because now S3 is in the non-basic variable part, and so it has a coefficient of 0 in the objective function, so this has become 0 instead of the 60 beforehand. So from this calculation we get 30, 15, and minus 5. Now we only have one minus value, but it's still a minus value, so it's not optimal yet. So we will have to check what happens here. Now this is a minus 5. This is in the third part. So check out. X3 is 30, X2 is 15, and X3 is minus 5. So X3 will enter the solution. Okay, X3 enters the solution. I have to check who leaves the solution. So I have to find the ratio test. So to do that, I have to find the new right-hand side values. Okay, all I have to do is just multiply these two matrices and get these values. Now, 16, 4, 4, 5 are my current right-hand side values. Now, these right-hand side values are for these sets. Okay, when S1, S2, X1, and S4 are ordered like this, we get these right-hand side values, which means S1 is equal to 16, S2 is equal to 4, X1 is equal to 4, and S4 is equal to 5. And for Xn, I have to find the current current constraint coefficients in the table. So these will be calculated by multiplying b minus 1 with n if I want to find all of them, but I don't want to find all of them. I just want to find the ones for X3, because X3 is what I'm looking for, because it's gonna enter the basis, enter the solution. So B inverse times AJ, which is the coefficients for X3, which were 1, 1.5, 0.5, 0.5, and 0. So this multiplication gives me minus 1, 0.5, and 0.25, and 0. Now, I cannot ratio test with minus 1, 4 over 0.5, and 4 over 0.25. 4 over 0.5 gives me the smallest value, which is 8. So the second one will enter, or sorry, leave. So which is S2. So X3 enters, S2 leaves. Now from here, I will just make sure that S2, which has, let's go and check, which has to, leave the solution. So all I have to do is just change this, let's go back, this part, B inverse part times AJ. This is what I have in the constraint, so I have to switch this one. S2 is leaving, so it's in the second row. So this 0.5 should change to 1, and everything else should become 0. So I will just change this part, this constraint coefficient part, into part of the identity matrix where the second value is 1. So this one changes into this one. All I have to do is just make the same iterations. I will make some row iterations over here, and I will make the same iterations for this B inverse, the current B inverse, so that it will change into the next B inverse. As I said, I can just take the inverse of the B matrix, that's okay, but it's gonna take a lot of time. This is a 4x4 matrix, so taking the inverse will take a lot of time. Instead of that, I will just calculate using the same row operations I make to change this constraint coefficients into part of the identity matrix. So what I need to do is just multiply by this 2, and this one will become a 1. So all of these values will multiply by 2 as well. So 0, 2, minus 4, 0. After the multiplication by 1, I can just add it over here so that this one will become 0. So add this one into this one, which will give me 1, 2, minus 8, and 0, as you can see over here. And I can just divide this by 2 or minus 2 and add it over here. Divide by minus 2 and add it over here. So divide by minus 2 is minus 1 becomes plus 1. This is minus 1. So add it down there, and this is minus 0.5. This is plus 1 and add over here, so that it becomes 0, 0, minus 0.5 and plus 1.5. So as you can see over here. So all I need to do is just take this constraint coefficient, take these constraint coefficients, turn them into identity matrix, and do the same operations without changing anything to the current B inverse, and I'll get the new B inverse in there, so that I can find the next steps B inverse to be able to calculate everything. Now, after we have calculated the new B inverse, we will check to see if the current basis where X3 has entered and S2 has left, which looks like this one, S1, X3, X1, S4. Now check over here. The order isn't, let's say numerical. X3 comes before X1. That can happen. It's not that important. I can change the order if I want to. I can just say that the new order is X1, X3, S1, S4. I can change the order. But if I change the order, I have to make sure that I change every matrix and every vector in the same order. But this is not that easy to do, so I advise you not to change the order when you're making the iterations, because it can get confusing very fast. So this is the current order because S2 has left and X3 has entered instead of it, and as you can see, S2 has taken X3's place over here. So we have to calculate the new values. We already know the new B inverse, it's over here. So the new W will be the current coefficients for the basic variables in the objective function times the current B inverse, which will give us 0, 10, 10, 0. So optimality condition, I have to find the coefficients for the non-basic variables for the xn. So all I have to do is just work through this formulation. I already have the W, so I can just multiply it with the n value and then subtract the Cn values. 0, 5, 10, 5, 10, which are all greater than or equal to 0. So yeah, this should be optimal. But I have to check the right-hand side values anyways, because the right-hand side values might be negative, which would give me, a chance to do dual simplex or just consider these, this solution infeasible. We'll see. B inverse, which I don't know, times B, the original right-hand side values. These are always the original values, okay? And the Cn is always the original values for these elements, okay? These are, as you can see over here, always the original values, these vectors. So CB, the N, the Cn. These are always the original vectors, original values for the current set, okay? The current set might change, so they're always the original values for the current set. Now, from this multiplication, I get 24,825. As you can see, they are the values for our current basic variables, and they are all positive, and the optimality condition holds, so this should be optimal. Then I calculate the Z value, which will be CB times B inverse times B. Now, I can do this in two different ways. CB times B inverse was W, which I can use here, just multiply it with B value, or I already know the B inverse times B, which is 24,825, and I can just multiply it with the CB. In here, we are multiplying W with B, but as I said, I just have these current B values, which I can write like this. I'll just write it over here. I can just write it like this, B dash. This is the current, this B dash is the current values of the right-hand side, and this B dash can be just multiplied by CB to get me the Z value. It will be the same value, it doesn't really change. So I have found the solution, 280 for the Z value, and I already know the basic variables values, so I should produce 2 units of X1 and 8 units of X3. That's it, and this is the same value we have found earlier. Now, this is faster in calculating stuff. Why? Because we have omitted calculating a lot of the parts of the table. There's still a faster way yet, we will see later on, but still, we have omitted calculating a lot of parts of the table, so it has given us a shorter time of calculation, which means that a faster solution, finding the solution much faster. Now, this one can also be useful for random starts. What is a random start? Well, think of the Dakota example once again, and I say to you, okay, you already know the answer. We know this is the answer, X1, X3, S4, S1, S4, but just forget about it, and let's look for the answer once again. But let's say that X1, S2, X3, and S4 are our basic variables. Does this set give me, let's say, does this set give me a optimal solution, an optimal solution? Is this basic variable set optimal? Okay, to be able to find it, I will just have to find all the values, the C, B, C, and B, and N values, according to these two sets. And from here, I can say that, okay, this is optimal or this is not optimal. I have to make iterations. We will see. Now, there is always a possibility of a random start like that, because you may have a solution at hand and you don't know if it's optimal or not. So you want to check if that solution set is optimal. Okay, you maybe said that, okay, we are producing these 3 items and we are able to produce these 3 items and I've been producing this item only. Is it optimal? Can you check? Yeah, you can check. But you have to know which variables are basic variables and which are not. As long as you know them, you can check everything. So let's just say that these are the basic variables, x1, s2, x3, and s4. This might be an infeasible solution as well. We don't know, but we will see if it's feasible or not. We will see if it's optimal or not by making iterations. Now, for x1, we know that this is a value of 60 in the objective function. x2 is 0, x3 is 20, and s4 has 0. For the xn parts, we have to find the objective function coefficients once again, which will make up to Cn. For S1, this is 0. For X3, this is 30. And for S3, this is 0 once again. We know the B matrix. For X1, it's 8, 4, 2, 0. For S2, it's 0, 1, 0, 0, and etc. And we know the N matrix. We have to just find the coefficients of the constraints for these 3 variables, and we will get these values. Now, from here, we need to find the B inverse matrix. Now, we have to find the inverse by hand, because we haven't come over here by doing iterations. We don't know which iterations have led us here. So we have to find the inverse of this matrix. How can I do this? How can I find the B inverse for this one? Do you remember? How do you find the B inverse? When you have a 4x4 matrix, how can you find the inverse of that matrix?
B'nin yanında bir tane identity matrix oluşturuyoruz. Aynı row ve kolumla sahip. Ondan sonra row operations yapıp identity matrix haline getirmeye çalışıyoruz B'yi.
Okay, very good. We add the identity matrix to the right or left. You don't, it's up to you, side of the B matrix. It's usually the right-hand side. And then we turn that B matrix into an identity matrix by row operations. And we check what happens to the identity matrix doing the same operations so that we get the B inverse from that identity matrix. So we have the B matrix over here, the identity matrix over here. We are making the row operations one by one, and at each row operation, we are changing the, right-hand side, the identity matrix itself as well. For example, in the first operation, we are just multiplying this row by 2 so that we can change it into 1. So this has become 1, and this will be multiplied by 2 as well. So it has become 2. After that, I will just take this 1 and multiply it by -1 and add it over here, and multiply it by -1.5 and add it over here, which will give me this, matrix. And for the right-hand side, for the identity matrix, it will become like this one. And we keep going and going, doing the operations, and we get this B inverse matrix. So I'm going to use that B inverse to calculate the W value. W is calculated from CB times B inverse, which is going to give us -5, 0, and 50, and 0 values. Now, from here, from this W, I can use it to find if the current solution is optimal or not by using the formulation, this formulation, optimality formulation. I will use W instead of this one. I want to calculate it anyways. And I will just use the current N and current Cn values, which will give me -5, 15, and 50. So -5. Okay, something isn't allowing us to be optimal. There is non-basic variable that needs to enter the basis. Let's go and check the first one because it's -5. Okay, this is the first non-basic variable. This is the second. This is the third non-basic variable. So the first non-basic variable will enter, which is S1. Okay, S1 will enter. Who leaves? Well, we have to find the current right-hand side. The current right-hand side is, as you can see, the current B inverse times the original right-hand side values is 8, 12, -16, 5. There's a minus value over here, but we don't need to check that minus value because we already know that it's not optimal. As it's not optimal, we don't need to do a simplex yet. So we have to check the optimality first. So we already know that S1 will enter. So we have to check the row for S1, the column for S1, and see what we can find to make the, ratio test. So this is the original column for S1, and this is the current B inverse, which will give me the current column for the S1, which is 0, 2, and 5, 0, 5, -1, and 0. Now, B inverse, you can think of B inverse as your time machine, okay? When you multiply something by B inverse, you get, and when you multiply the original value, the initial table value of something with B inverse, you get the current table values for it, okay? B inverse is your time machine. It can revert the original values into current values, okay? So when I multiply B inverse with AJ, the original constant values for S1, I get the current constant values for S1, okay? B inverse changes original into current always. So these are the current values, and I will just make the ratio test 8 over 0.25, 12 over 0.5, -16 over -1, which is not going to be tested, 5 over 0, which is not going to be tested anyway. So I will get 24. The lowest score is the lowest ratio is 24, which means that S2 will leave the bases. Why? Because this is the second row, and let's go back. The second row belongs to S2, so S2 will leave the bases. So after S2 leaves the bases, we will try to find a new B inverse, and then we will try to find the new iteration anyway. But this is the same thing, okay? After we have seen who enters and who leaves, we will just make the same iterations over and over again to get to the optimal value, and we will get to the optimal value in the end. So let's have another example. Now in here we have 6, as you can see, variables, and over here down here we have 9 variables with the added S values. So these are our select values, S1, S2, S3, and these are our 6 decision variables. We want to maximize this one. So we start with the simple stuff, the vectors. Now we know that the B is S1, S2, S3, so it's going to be identity matrix. We know that the N is going to be over here, those 3 by 6, this 3 by 6 matrix, which will give us all the coefficients of our decision variables, and our Cn is going to be 1, 2, -1, 1, 4, and -2, and our CB is going to be 0, 0, 0 anyway, as you can see over here. We are multiplying those CB and B inverse values to get the W, and then from here we're going to get the optimality condition, check if this is optimal, and see that it's not. So the most negative value is -4, so as you can see, X5 enters because -4 belongs to X5. So X5 enters, okay, the right hand side is 644. Okay, as I said, the B inverse is a time machine, but we are not using the time machine yet because we are in the initial solution, initial step. So the time machine won't work. So it will just give us the same values again and again and again. So this is 644 for the right hand side, 102 for the constraint coefficient. So the ratio test will be 6 over 1, 4 over 0, 4 over 2, which is going to be the smallest value is going to be 2, which is the third row, which means that S3, the third decision variable, the third non-basic variable will leave the solution. So X5 enters, S3 leaves. As S3 leaves, I'm going to have to change 102 into 001 because 102, this one, belongs to X5. And as S3 leaves, this value should become 1. So this will change into 001, as you can see over here. And I will change B inverse with it as well, which will give me the new B inverse. This is the new B inverse. And my current set for basic variables is S1, S2, and X5. Okay, let's keep going then. What happens in the next step? I already have the new B inverse, so I'm going to have to calculate the new W, which is going to be CB times B inverse, which is going to be 002. Okay. Now, from this one, I have to check the optimality condition. So I will just multiply this W with N and multiply subtract Cn from it. As you can see over here, this is W multiplied with N and subtract Cn, which is going to give me -1, -2, 3, 1, 2, 4. Now, The most negative one is over here, -2. So x2 will enter. Why? Because remember this one. We already know that x5 has entered and s3 has left. So this belongs to x1, x2, x3, x4, s3, x6. So this is for s3, this is for x2. So x2 enters. So who leaves? Well, we will see. We have to make the ratio test. So to be able to make the ratio test, we need the right-hand side first. So b inverse times small b, which is 4, 4, 2. We also need the constraint coefficients. For whom? For x2. So constraint coefficients for x2 will be calculated by using our time machine, which is b inverse, with the original x2 values. Okay, time machine times the original x2 values will give us the current times values for coefficients. Coefficients for constraints. So 1, -1, 0. These are my coefficients in the constraints, and these are my right-hand side values. There is only one feasible ratio which is going to give us 4 for the first row, which means that S1 leaves. So X2 enters, S1 leaves, which means that I have to change this 1, -1, and 0 values into 1, 0, 0. Well, it's simple because all I have to do is just add this one to the first row to the second row, and I will get 1, 0, 0 anyway. So all I have to do is just add first row to the second row, which is going to give me the new B inverse, the new time machine. So I'm going to use this one to check optimality. Okay, I have the new B inverse. I will calculate the new W, which is going to be 201. Okay, and from this 201, I have to find, calculate the optimality condition. I multiply this 201 with the current N, and remove or subtract the current Cn, which is going to give me 124, 215. All of them are greater than or equal to 0. So this is an optimal solution. I have found the optimal solution over here. So at every step, after the calculation of B inverse, if I found the B inverse, I calculate the W value, and using that B inverse, I calculate every current coefficient that I need to find. Okay, all those current coefficients can be found by using the B inverse, our time machine. Okay, and then at one point, if I find the optimal solution, I'll say, okay, we are done here. We don't need to calculate anymore. We can just find another, thing to do with that revised simplex, which is going to be our, next 2 or 3 steps. You will see. Well, what if it was a minimization problem? What if we had a big M? Well, we can do the big M thing normally as well. There's no change in that, part. If we are using the, revised simplex, we can just use that big M normally anyways. And we don't need to change anything. We will just use those M values in matrices. That's all. As you can see, this is the basic variable set, S1, A2, A3 for this one. And we have the X values as well. And we will just make the calculations in the same way. The only difference is we have M values in our matrices, and it's going to be a bit more complex because I have to deal with M values. But it's not that hard. Okay, it's just like big M with less calculations, hopefully. Now, as you can see, we have M values, we have found the W, we have calculated the optimality condition, and we are going to check who is the greatest, who has the greatest positive value. Why? Because it's a minimization, so we're going to get rid of the positive values, which is 4m minus 1, so x2 enters. Okay, who leaves? Well, I have to find the, I have to calculate the ratio test, find the ratio test, and found out who leaves. But it's easy because it's the initial step, so it's 466 for the right hand side and 113 for the constraint coefficients. So the ratio test is going to give us 4, 6, and 2. So A3 leaves, the third one leaves. As you can see, A3 leaves. So if A3 is leaving, then I'm going to change this 113 into 001. So changing 113 into 001 and doing the same thing for our B inverse, our time machine will give us the new B inverse. Now, using the new B inverse, I have to calculate the new W, which is going to give me a value with an M, 1 minus 4m over 3 over here, as you can see. And now using this new W, I'm going to have to calculate the optimality condition. Again, there's a positive value in here, 2m minus 3. Now, as you can see, with the addition of M, the calculations, the mathematics multiplications are getting a bit more complex as expected, but still can be doable. Okay. now we have a new m value over here, positive m value over here, and another one over here. This is bigger, so we know that x1 will enter the solution. So we have to find the current right-hand side using our time machine. With the old initial right-hand side, we find the current right-hand side, and using our time machine, the B inverse, with the initial coefficients of the constraints for the entering variable, which is x1, we find the current ones, which is not different. It's the same. It's pure luck. Okay, it's not something that is calculated. It's pure luck. It can happen like this, but it's the same as the original ones. So we can just make the ratio test normally. 2 for 2 over 1 to 0. They are both 2s. So we have the same ratios. We have to pick which one is entering and which one is leaving. And originally, I would just chuck A2 out, but in here, in the operations, we have chucked S1 out. Yeah, it's okay. Probably A2 will be leaving later on, or we won't need it to leave. But we could have left A2, chucked A2 out of the solution. But in here, S1 leaves. Okay, maybe I wanted to make the iteration longer. I don't know. But still, S1 leaves. So 1 to 0 becomes 1 1 0. When I'm changing this 1 to 0 into 1 0 0, I have to change the B inverse as well, the time machine as well, so that it becomes the new B inverse. So what I have to do is just find a new W, find a new optimality condition, and check if it's optimal. We are doing the optimality condition calculations, and see that there are no positive values over here. As you can see, this is the new B inverse. Okay, and all I have to do is just multiply it with CB to find a new W, and then use this formulation to find the optimality condition, and it's optimal. We don't need to change anything. Okay, it's optimal, and I have to find the Z value and right-hand side values as well. The right-hand side value is easy to calculate. This is B inverse times the original B, which is going to be 202 for x1, a2, and x2. A2 is 0, so we have no problems there. Okay, we are cool in that, but we have to calculate the Z value as well. Now, the Z value, while we are calculating it, we have these, the left-hand side value, we already know those values. So we have to just, the W value is going to be multiplied by the, 466. You remember that one? So we are gonna get a new value from here, but we also have to add 12m. Okay, why do we add 12m? Because we already know there's a 12m over here that we didn't use in the calculation, because this is just a constant number. We have added this to find the standard form, to find the initial starting table, but this is here. Okay, we shouldn't disregard this 12m, because when you calculate this, when you make calculation over here, you will get here 8 minus 12m. So with the plus 12m, you will just get 8, because you shouldn't have m in there. You don't have a values, so you shouldn't have m values in there as well. So the Z value is 8 with the added 12m, thanks to the added 12m that we haven't forgotten, which is coming from over here. So with this 8 value, we have completed, making the minimization as well. As I said, this is just like big M, normal big M iterations, but we are using less and less computational time, because we are not calculating every M value, every, coefficient, which is going to have lots of M values in them. So we are, saving time. So now we're gonna see the table form for Revised Simplex, and the table form makes everything faster, even faster than what we have seen so far. And we will be using tables once again, hence the table form. But there will be, the tables will be a lot more constricted, smaller versions of their original ones, okay? We will have the basis inverse part, as you can see over here, the right-hand side, and the xk part. Now, each of these are just parts that can be calculated easily using the original values, and then we will see how we change them step by step. Now, we have the Dakota example with only 3 constraints this time. The fourth constraint is not here, and the standard form of it. Now, we will just change this into the table. Now to do that, we have to write the side, the values, the basis inverse, the right-hand side values. Now, in the basis inverse, we know that this is the part where we take the basic variables and use their coefficients. So these are your objective function coefficients, and these are your, let's say, initial table constant coefficients at the start. We'll get to B inverse soon enough, because this is going to become B inverse as well. This is B at the start, but it's equal to B inverse. So this is going to be B inverse sooner or later. And these are the right-hand side values. Now, we already know that we can just use this part, W times AJ minus CJ, and we can use the N instead of AJ and CJ over here, as you can see, to get the, to find out who enters the solution. This is something we already know. And X1 is entering the solution. We already know that. Okay. X1 is written here. This is the one that's entering the solution. Now, up until here, we didn't know anything about the entering or leaving variables. Now we know who is entering the solution. This is X1. So this is minus 60, because X1 has the, as a non-basic variable, has the objective function coefficient of minus 60, and it has 842. And here we have the right-hand side value, so we just write the ratios. That's it. Now, normally you would have lots and lots of more, not lots of, but still at least 2 more columns, and we are just ignoring them. We don't need them anyways. So we're writing columns when we need them. And from here, you can just pivot and see what happens. So all we have to do is just get this minus 6842 into 0001. And we can do this by just using the, column row operations, sorry. So all we have to do is just divide this 2 by 2 to get to 1, and then just add or subtract the, reasonable amounts to get all these values into zeros. So when we do that, everything over here will change. Everything in the basis inverse and everything in the right-hand side values will change, and they will be our new table. So we don't need to calculate the basis inverse values, these values, by multiplying the B inverse with the appropriate starting value anymore. We can just use this iteration, the turning into the turning into the identity matrix operation, to find the values for everything over here, for right-hand sides or for the basis inverse. Remember, the right-hand side values were calculated like this one. We had to take the B inverse and multiply it by the small b to get the current, B bar, current B right-hand side values. But we don't need this anymore. All we have to do is just calculate this, operations, row operations, and find the part of the identity matrix that we need to find, and the right-hand sides themselves will change into that as well. So all we have to do is just change it into 0001, and these values will appear by themselves. Now, we don't need to calculate them anymore. What we need is just to calculate who is entering them. Okay, let's check the optimality then. W times n minus Cn. So we will get 30, 15, and minus 5. And minus 5 is the one entering. So x3 is entering the solution. So we will write x3 over here. And we will write the values for x3 down here. Now, the values for x3 are over here. And from that one, we will just find what's going on with the original value. So we will do the ratio test, who is entering and who is leaving. Well, x2 is entering, but who is leaving? The second one, so s2 is leaving. So we will just change this 0.5 into 1, and everything else will be changed into zeros. And this part will change by itself. We don't need to make any more matrix operations over here. We just need to use the table form and make the row operations themselves. So we'll get this part. Now over here, we already know this is the solution because we remember we have memorized the solution by itself. So 280, 280 is the solution we all know, but let's see if this is optimal anyway. So we have the W value over here, which you can see over here. And we have the N value, which we will take from the initial part, and minus the Cn values, which is the, again, from the initial table. And we have 10, 5, 10, which are all non-negative, which makes this the optimal solution. So basically in the table form, you just make iterations normally, but with only the needed parts. You don't need anything else. You just use the needed parts. You don't use anything else. So All you have to do is just calculate those parts and nothing else. So the another subject with revised simplex, which in my opinion is the most useful one, the one that you will have to check and see all the time, is the sensitivity analysis part. Now, with sensitivity analysis, we already know that we can use, for example, we can use the graphic method, for example, but what if we have more than 2 variables? So we need something much stronger. Now, with this version of revised simplex, or with the revised simplex, let's say, there's another version of it. With revised simplex, we can just do the sensitivity analysis easily, because what we need is just to have the optimal solution, the variables for the optimal solution, just that's enough. We can calculate the values anyway, but as long as we know who are in the table, who are in the basis for the optimal solution, which for example, Dakota is x1, x3, and one of the s's, I think. Yeah, s1, x1 is x3, and s1. Now, these are the basic variables. From here, we can find the basis inverse, the B inverse. Now, the B inverse, this is a trick, a shortcut, let's say. If you have the optimal table, all you have to do is just check the slack or artificial variables, and anything under them is the basis inverse. So this part here, 1, 0, 0, 2, 2 minus 0.5, minus 8, minus 4, and 1.5. This is the basis inverse. This is the inverse of B. So using this, we can calculate anything we want. Okay, how do we do that? Well, let's say that we are changing a value in the original initial solution of tables. So instead of 48, we're going to get 48 plus something, plus 5, plus 10. What happens if we change it by 20, for example? Or minus 10, minus 12, something like that. Or instead of 20 over here, 20 plus something or minus something. Now, to check this, we have to figure out, or we have to use a new variable, which is mostly going to be called delta, you'll see. And we will use that delta and calculate ranges for that delta, both increase and decrease ranges for the delta. Now, how do we do that? Of course, first of all, start by finding out all the necessary, calculation methods for revised simplex, not the table form, but the normal revised simplex algorithm. So we know that there's the B inverse over here. As I said, this part is the B inverse, the part under the S values. So this is the B inverse. We also know the right-hand side. These two are multiplied to get the right-hand side. Now check over here. This is the original one, okay? The original right-hand side, we know that. And this is our time machine, the B inverse, and giving us the new right-hand side. And over here, we have CB, B inverse, and minus Cn. Now, we are rewriting them apart because we are going to do the analysis on them. So we don't need W right here. We need to see CB if we are going to talk about the, change in CB. And there will be no change in Cn, actually. At least for the S part. There can be, of course, change for the X parts, but there are going to be no change for the S parts. Same goes for CB's S parts, of course. Think about it. In the original model, there are no S values in the objective function, no S coefficients. And you cannot write 5S1 over here. What happened if the coefficient of S1 was increased by 5? Okay, no. As long as we're not changing the question itself, for example, you could say something like this, then that can happen. What if we are going to sell our free time? Okay, let's say that S1 is, or this constraint is something to do with, let's say, I don't know, finishing time, carpentry time, something like that, and we can just rent this out, whatever we don't use. Or if this is the raw material and we can sell this raw material, then yes, we can add a value over here, but then it will be in the model anyways. It won't be an S plus value over here and no value over here. It will be in there anyways, but if you're just thinking of this right now, then yes, it can change. Of course it can, but still not likely. If it's something that can be solved, it will be in the, model anyways. It will be, in the initial constructed model anyways. So we usually don't change the S values because they are added later on. They don't have any values in the Z, the objective function. So yeah, as long as we're not changing the rules of the, model, we're not doing anything to sell S or A or E values anyway. So we're not going to change them. And the same goes for the S values on Cn, of course. But still, it might happen, but not likely. So Of course, if you have forgotten to use them and then you're adding them later on, yeah, that can happen, but still unlikely. Very low percentage, I would say. Well, still, let's go back. So we have the CB, the coefficients for the basic variables in the objective function, the N, non-basic variable coefficients for the constraint, the Cn, non-basic variables for the objective function, variable constraints for coefficients for the objective function, and we have the calculation over here. Now, if I change something, for example, let's go back. If I wanted to change this 20, it would mean that this 20 is changing as well, okay? By the way, this 20 is not the same as this 20. This is the right-hand side 20. This is the small b 20. Don't mix them up because this 20 is not changing. This one is only. So if this 20 changes, I would just say, okay, 20 plus delta. Add a delta value here, or theta, eta, whatever you want to, alpha, beta, anything is fine. But still, 20 plus something, 20 plus alpha, for example. Now, this alpha value would be calculated in the matrix multiplication, and they would give us some alpha values on the right-hand side, the new right-hand side values, the current right-hand side values. And from these alphas, I would say, okay, I know that the right-hand sides cannot be negative, so any alpha value I find here cannot make these values negative. So I have to find the ranges accordingly, and I will just calculate accordingly. For example, well, it starts with 20 anyway, so it says the 20 plus alpha. Now, when you take the multiplication, when you make the operation of multiplication, you get these values. Now, 24 plus 2 alpha, 8 plus 2 alpha, 2 minus 0.5 alpha. Okay, now as you can see, 24, 8, 2, they don't change. 24, 8, 2, they are still there. But we've added alpha over here now. And different amounts of alpha, plus 2, minus 0.5. From here, I can just find which values of alpha still gives me values of non-negative values for right-hand sides. For example, if I take alpha as low as minus 4, this value would become 0, this value would become 16, and this one would actually increase. I don't know, minus 4, I said yes, so it becomes 4. So this one becomes 0 at minus 4. If I take it less than minus 4, for example, minus 5, this one becomes a minus 2. This is still plus, this is still plus. So this is, breaking the feasibility condition. So alpha cannot be lower than minus 4. What if I take it higher? Well, if I take higher values, positive values of alpha into, higher values, these two will keep getting higher and they will not change. So it's okay. So I have to check this one. If I take alpha to, I don't know, value of 2, this one will become 1. If I take it to 4, this one will become 0. If it's anything greater than 4, this will be a negative value, which I don't want to see. So I cannot find a negative value in here. So alpha can be at most 4. So alpha is between minus 4 and 4. Okay, this is what I've been looking for. This is the sensitivity analysis. The value for alpha between the least value or highest value of change, the increase, okay, the allowed increase and the allowed decrease values. So yeah, what about, I don't know, another value, for example, beta, 8 plus beta. Okay, if I take 8 plus beta, so I will make the calculations once again, the same B inverse, the same right-hand side values with the change of adding a beta over here, and I will get these values. So you can see 24 minus 8 beta, 8 minus 4 beta, 2 plus 1.5 beta. This one will give me the negative limit. These two will give me one of them. This will give me the positive limit. So with beta greater than 2, this one will become negative. With beta greater than 3, this will become negative. So I will take the 2 value, the lowest of the 2, as the limit that I can take and increase beta up to. So beta is going to be less than 2 because of this one. And with this one, beta is going to be greater than minus 4 over 3, because all I have to just see that if beta is 4 over 3 minus 4 over 3, this one will become 0. So this has to be minus 4 over 3 at least. So beta is going to be between minus 4 over 3 and 2. These are the right-hand side values, okay? What about we change both of them at the same time? Now, this is becoming a bit more, let's say, complex. Okay, if you change 2 of them at the same time, you will have different, let's say, for here at least 3 different, limits, upper and lower limits, and you have to find something that depends on each other. So if you want to find something for alpha, it will depend on beta and etc. So let's check. If you make the calculations, you will get 3, as I said, equations, or not equations, but inequalities, because they have to be greater than or equal to 0. So to be able to hold all these three, we have to find how alpha and beta can be, picked, chosen. So as you can see, for the first one, I can just divide it by 2, and these values can be divided by 2, and I can write this one: 4 beta minus alpha is less than 12. For the second one, again, divide them all by 2 and write 2 beta minus alpha is less than 4. For the third one, well, I have to multiply it by 2, so I get rid of the 0.5 and 1.5 values, and then I can just write alpha minus 3 beta is less than 4. Now, I have 3 different inequalities with alpha and beta, and I have to form something from them. I can just leave it like this maybe, but still there's something that can be done about it. For example, if you add 1 and 3 together, okay? By the way, when you're adding some inequalities, you have to make sure that their signs are in the same direction. This is very important. This is very, if you don't do that, you will get a wrong solution, because if the direction is different, then there is no meaning in adding them. So when you add 2 of them together, by the way, you don't ever subtract, you always add them, because if you subtract them, there can be a mistake over there. Instead of subtracting them, you have to add them. It's easier that way, but still. Now let's see. This part added to this part. These 2 values are smaller than these 2 values. So when you add these 2 values, you will get lower value on the left-hand side anyway. Let's just assume that we are making something like this. Let me just make sure that you understand what I'm talking about. Let's say 1 is less than 5 and 0 is less than 6. Now, if we add these 2, I will get 1 is less than 11, which is correct. But if I subtract these 2, which is wrong, I'll get 1 is less than minus 1. What? No. So you cannot subtract those values. You always add those values, so you don't mix them up. So we are adding these 2, okay? And if the signs are wrong, you can just multiply any one of them by minus 1 and add again. That happens. It's not that important. You can multiply the rows by, or divide the rows by any value you want to be able to cancel them. Make sure that they cancel each other. But still, these are row operations, simple stuff. So when we add these 2, okay, the alphas will cancel themselves out, and we will have just 1b left over here, 1 beta, which is less than 16, as you can see. And you can add the second and the third together, which means that minus b is going to be less than 8. Let's inverse it. Minus 8 is going to be less than b. So beta can be between minus 8 and 16. But it still depends on alpha. You can't just pick one and keep going. You have to see how alpha can be, written dependent on b, beta as well. So what I have to do is just find how alpha can be written. Well, alpha will be left alone, and we'll just write the beta values. For example, if I take this alpha and send it to right-hand side, and take this 12 and send it to left-hand side, I will have 4 beta minus 12 is less than alpha. Same over here, send the 4 over here and alpha over here. 2 beta minus 4 is less than alpha. And send the 3 beta over here. Alpha is less than 4 minus 3 beta. So I have these 2 values in there as well. So they should all hold. As long as these all hold, I'm okay. So this is how I can, do the, find the allowable range for more than one. Let's say with two or even 3 of them. But you have to make sure that you calculate these for the right-hand side only. If you want to mix and match with the, objective function values, you will get more and more, confused along the way. 2 of them is enough. 3 is just overkill most of the time, but still, this is pretty good practice for linear algebra as well, I guess. So you may not always find such clear inequalities. There might be some, unclear versions, so you may just have to leave it like this at some times. That happens. It doesn't really, it doesn't say that you have done it wrong. It's okay. It might be like that because not all, let's say, rows can cancel each other like this one, as neatly as this one. So it might happen that you may have to leave it as this, like this one. But try to leave it as in the simplest form as possible. So writing it like this, 24 plus 2a minus 4, 8 beta is greater than 0, isn't as good or slick as writing it like this, 4 beta minus alpha is less than 12. This is far better than this one, and more understandable, of course. So what about row 0 values? What happens if we change them? Well, if you change them, you can just find the you can just calculate the optimality condition and find the values for that optimality condition and go from there. Well, we have the B inverse, the basis inverse, and the n values, and you can just find those values anyways. And what if something changes in CB or CN? Now, we will not use W, CB times B inverse, but we will use B inverse times N, because this won't change. We are not changing constraint coefficients yet. You can change them as well if you want, but we're not changing them. We are changing CB or CN, because these are row zero values. These are objective function coefficients values. So we are going to change them. Let's start with changing 60 plus A. Now, this is for x1, if you can remember. x1 is a basic variable, so 60 plus A is changing. And this is going to give us a new solution with A's in them. We will just calculate all the, make all the matrix calculations as normal, and we will find new values with A's. Now, we know that for the optimality to hold, all of these should be greater than 0, greater than or equal to 0. So what happens? How can I change these into zeros? I will just check each of them one by one. 10 plus 1 point A is greater than or equal to 0. So A should be greater than minus 20 over 3, which is like 6.666 minus. 5 plus 125A should be greater than or equal to 0, which means that A should be greater than minus 4. Okay, this is a better constraint than this one, because this is more constricting, as a constraint should do. So minus 66 is not a good lower bound, but minus 4 is a better lower bound for this one. So this one will get eliminated. And for the last one, 10 minus 0.5A, well, as long as A is less than 20, I'm okay. So A is less than 20, which makes A between minus 4 and 20. And same for 20 plus B, another basic variable. I'll just calculate all the values after the calculations. I just calculate and make sure that all the values are greater than 0, in which they are, where beta is greater than minus 5 and less than 2.5. And what if we do them together? Well, we again get some inequalities with two unknowns, and we have to solve those inequalities with two unknowns. As you can see, this is the simplest form they can be written. And by, for example, let's just say I can just multiply this by 3 and edit over here, or multiply this by 4, edit over here, and etc. I can just make other iterations in there as well and see what happens. But 1 and 3 and 2 and 3 are the ones we are looking for, because in here you cannot make any summations or divisions and multiplications and summations with 1 and 2, because they have the same let's say orientation, alpha minus beta, alpha minus beta, but we have beta minus alpha over here. They have the same size, so I don't need to change anything. I'll just have to add over here. So I'll have to do just multiply this by 3 and edit over here, and multiply by this 4 or edit over here, or multiply by 2 and edit over here to cancel the betas and leave an alpha. That depends on how I want to go there. Okay, I can just multiply by 2 and edit over here and cancel the betas as well. But still, by doing this, I can find lower range and upper range for alpha and beta. For example, for alpha, it's minus 32 infinity, yay. But for beta, it depends on alpha. So if alpha is going over infinity, beta can go as much as it wants as well. But if alpha is going minus 30 over to minus 30 or something like that, beta cannot get those bigger values, because it has to remain small and small. So they are dependent on each other. I can just figure out how they work together by just doing some linear algebra, operations, row operations and stuff. Now, what about the CN values? Well, these are easy to calculate. Okay, why? Why are they easy to calculate? The CN values, let's just go back over here. So we already have a calculation over here. So CN values are easy to calculate. Okay, why? We already know the answer, by the way. Why are CN values so easy to calculate? Well, first of all, if you have the optimal table, they're just written there, because CN values are your what? Reduced costs. So reduced costs are easy to calculate because they're just written there. For example, for Dakota, it was 0, 10, 10. So we can just see how that works by just or 10, 5, 10, whatever, which one is, I don't know, remember the exact one right now, but still there are more iterations. Let's go back and see. Yeah, 0, 10, 10, as you can see, or 5, 10, 10. Yeah, Because these values, that's 0 times 10, of course, 5 times 10, these values are reduced cost, because this is how much we need to increase their values to be able to get them into the solution. But we know that S2 and S3 will not be in the solution anyway, so it's not the reduced cost I'm looking for. X2, 5, this is the reduced cost. If I increase X2 by 5, the coefficient X2 by 5, it will enter the solution. So I don't need to make any iterations in that. I don't know the solution. X2 is minus infinity to plus 5. That's all. I don't need to make any iterations. So for Cn, for the allowable increase and decrease values of the decision variables, the non-basic decision variables, I don't need to calculate anything. I don't know the answer by just looking at the optimal tables. So what about adding a new variable? Now we can add a new variable with revised simplex, just like doing the dual, just like in the dual form. But still, when you add a new variable, this is going to be considered a non-basic variable. Okay, why? Because simple stuff. We have how many basic variables do we have in a model? This is something we all know. How many basic variables do we have in a model? It's equal to the number of constraints we have, right? Yeah, it's equal to the number of constraints. So when you add a new variable, well, you're not changing your amount of constraints, so it cannot be a basic variable. It has to be a non-basic variable. So we will treat it as a non-basic variable and add it at the end of the n matrix. All those coefficients will be added to the n matrix, and its objective function coefficient will be added to the Cn vector. So this Cn will be like this with 15 added value and 1, 1, 1 as the added values in the n matrix. Now from here we can just check the optimality once again. We already have the CB values over here, the B inverse over here, and the new n and the new Cn, and we're going to check. Okay, it's optimal. 10, 5, 10, 5. We don't need to do anything with this one. This is added and it's optimal, so we're done. If it wasn't optimal, we would just be, using the table form, for example, and calculating the iteration, making iteration by itself. But we can just check if it's optimal instantly by just multiplying these matrices and, finding that vector over here and just subtracting this vector of Cn values from the vector we have found by calculating over here. So this is actually easy to calculate, but if it's not optimal, then we have to make iterations, and we're going to have to use the table form or the simplex algorithm, whatever we want to use or whatever we're allowed to use for that one. But still, as long as we are adding a new variable, it should be considered a non-basic variable all the time. You cannot add a basic variable into the model by itself. And adding a new constraint, we have already seen this in dual simplex. It's the same thing. If the constraint holds for the current values, then we don't need to do anything. It doesn't hold, just go for dual simplex. We can just go for the negative right-hand side value and use the dual simplex because it's already an optimal solution in here anyways. So this is it for now for this part.